Hi, welcome back. So we're in chapter 5, prediction by probability, the outline of univariate concept of probability to discuss a probability of a continuous value. We have established the basic and fundamental knowledge in understanding the meaning of probability density function with some certain examples. Now we're going to expand that to include also the cumulative distribution function, which we have discussed earlier on in previous examples concerning the discrete random variables. Any probability with a capital letter of f that indicate cumulative distribution function of a variable x. Now this x could be discrete, could be continuous. Usually it is actually indicating the probability of x to be less than or equal a certain value of x. So you have to visualize that. You have to understand the meaning of cumulative distribution function based on this symbol of less than or equal certain values. Cumulative distribution function of a is equal to the probability of x to be less than or equal a. By defining the value a in this interval from x1 to x2, say this one, and the cumulative distribution function, what it tries to find actually the area under this curve in here. Now this could be also from a discrete random variable perspective from x1 to x2. Now let's take a quick example just to show you the concept in general. Let's assume that you are given a probability density function f of x, and what you are asked to find actually, let's say we want to find the f of 1. Also you are asked to find the f of x just in general. The graphical presentation of the probability density function here. What we are given first, we want to find the cumulative distribution function of x equal to 1. So to write this from mathematical perspective, that we are talking about the integral of this probability density function, things to be 1/8. So the area under the curve, the cumulative distribution function, given that x less than or equal to 1 should be equal to 1/8. To find the f of x, get rid of this one and assume this value happens to be x. Well, how to do that? It's the same exact concept by taking the integral from 0 to this x. That will be 1/8 of x cubed. This is the actual answer of the second part. Now to write down all what we have found in form of cumulative distribution function, and this is a very important thing. This way we write actually what's so-called a cumulative distribution function result usually. Let's take one more example. What is the f of x? Well, the approach, first of all, as we said, we have to graph. We are asked for the cumulative distribution function for this. Well, let's try to break down this particular square. And let's choose a value of x here. What we've got the f of x, the cumulative distribution function, should be equal to x, which is this particular value here. Like if this is x, will be x minus 0 by 1/4, so that will be 1/4 of x. This is the first part. Now let's extend now to take another part. Let's choose x now to be here. This entire area, it's actually take two probability density functions. So the wise thing to do, I think, is to look at this point up to 1 here as one area here, and then the other one, it's this area here. We've got the f of x should be equal the following. This is my first area here. Well, the area for this square, it is 1 minus 0 multiplied by 1/4, which is 1/4. You will get finally 120 multiplied by x power 4 plus 4. Now to finish up, you have to make your conclusion clear. This is the way we write the cumulative distribution function. I hope the idea is clear in principle. Now, in a different part of the quest to understand probability, maybe sometimes we are asked actually to find the median, the quartile or percentile probability from a probability density function or cumulative distribution function. Let me show you what I mean. We are asked to find the median, or sometimes it's called quartile 2, the second quartile. In general, median means it it is the half of the data set. It represents a point where it should be half, where this represents the m. Now, what does that mean from probability density function perspective or cumulative density function? Well, it represents the area, which is going to be equal to half. So it's going to be the cumulative distribution function of m here. It must be equal to half. In other words, I can write it down as if from minus infinity all the way to m of the f of x in terms of the dx, it just equal 1/2. The second example maybe I could share with you is the following scenario. And then what we're trying to find is something called the lower quartile. So lower quartile is equal, or LQ, which is usually known as the first quartile. Well, the first quartile, it represents 25% of the data set, which is 1/4 data set. So it should be somewhere around here, for example. So again, we're trying to find the area, the probability of the area under this curve. And therefore, I can say, well, this the integral from minus infinity all the way to q1 for the f of x in terms of the dx, it just equal 1/4. Maybe also we can look another case called the upper quartile. It should be somewhere here, quartile 3. The integration from minus infinity to q3 of the f of x in terms of the dx should be equal to 3/4. And the last case, maybe you can ask about the percentile. Well, could be 25%, could be 30, could be 65, could be 95. It depends on. So the PN could be any point within this interval, which is going to be the area under the curve. The number you are interested in divided by 100, that is the meaning of percentile then. Well, bring the same idea that mean I'm going to start from minus infinity to this P of n for the probability density function will be actually equal to n over 100. Well, what we're going to do next, maybe let's take an example. We have variable x that has a PDF of probability density function as follows. What we are asked to find is the median. You get this graph here, okay? Everything below the median, the area should be equal to half. By taking the integral of this PDF from -1 to the median, which I don't know the value yet, and then we got 5 minus 2x in terms of the dx is going to be equal to half. You will get the m could be equal to 0 or could m be equal to 5. If you look at the graph quite carefully, the median is equal to 5. This is not going to be within the range. It means the median happens to be 0 in this case. So we will choose that the median is going to be equal to 0 in this case. How about getting the second question, getting the first quartile? Well, the concept is the same. Nothing should have changed. Quartile 1 should be somewhere around here, like 25%, right? So if this is Q1, for example, so everything below this graph, the area is going to be 1/4. Now, obviously from the graph, I cannot choose Q1 to be this one, so it's going to be the second part, which is minus 0.54, which is going to be this point here. This is how actually you can use the knowledge of cumulative and probability density function to find the median Q1, Q2, or Q3. Now, what we're going to close on, that is to discuss finding the mode. And what the mode is, basically the mode of a random variable x is the value of x below the highest point on probability density function. So if you look at this graph, it's obviously we can see this is the highest point. It means this value of x2 represent the mode. When we look at this, we could see that the point here at x1 represent the mode in this particular graph. Well, if you look at this particular graph, you could see there are two modes. That's x1 and x2. In this case, we call a binomial mode. In this case, we have no mode. We said the mode is the highest under the point. Well, it means the mode should be here, somewhere around here. But what is it exactly? So if you bundle with x1 and x2, to find this is where we need to get back to the idea of derivative, as we say. So if we want to find this tangent line that is exactly have the slope of 0 at this point, it means by taking the derivative of this function and then when it is equal to 0. So this is a quick discussion on the idea of the mode. Maybe in many cases cases we are asked to find the mode given the probability density function. Imagine this is a component, electric component, and its model, its lifespan, between 0 time and 2 minutes. And then for some reason we would like to see what is the mode exactly, say what is the peak time of that component as it is running off. Well, first thing I like to do is to draw actually the functions. We need to find this mode, and the best way to find this mode, that we need to find this tangent line after we get the derivative of this function, the PDF here. We get the value when the derivative is equal to 0. So we believe now the mode of this variable is going to be 1.5. This is the way actually how we operate to understand the mechanism of finding the mode for a certain problem. Okay, now let's proceed further and discuss now something that we should be very much familiar with, and that is to find the mean or the expected value, and also the variance. Actually, we have seen when we've got like such a discrete kind of value, what we should do. Let's assume here we got this discrete kind of variable looks like this. This is x. Let's assume here we've got a graphical representation for probability density function looks like this is the f of x. So let's first of all see what we have done earlier before. When we discuss the expected value given the variable is a discrete, like in this case. Well, in fact, we need to know that the sum of these probabilities should be equal to 1. Given the fact it's a continuous kind of variable, we cannot really use the exact sample of sum, so we're going to use integration from minus infinity to infinity. Integral of f of x should be equal to 1. So you could see the similarity in this case. Let's see the mean. How did we actually capture the mean? Or in other words, we say the expected value of x. If you remember the formula, we said, well, that is the sum for all x. Every observed value of x, which is in this case 1, for example, and multiplied by the probability of x, so by its probability. That's exactly what we did. Well, same concept we can do here. That means the expected value of x, that's nothing but the integral from minus infinity to infinity, given every observed value of x, and just multiply it by its probability f of x, and then you will get the mean. And finally, if you want to get the variance, we said that is equal to the expected value, the x square, minus the expected value of x, all is squared. So you get the expected value of x and then you square. But the question is, what is this, the expected value of x squared? It's just equal to the sum for all x, of course, but square it multiplied by its probability. Well, the same thing I can do here in this case by just taking the expected value of x squared, which is equal to the integral from minus infinity to infinity, taking every observed value here in x squared multiplied by the f of x. And the formula here of the variance is to sustain the same for both cases. I think the best thing to do is to take a practical example. Let's assume for some reason you get a continuous random variable x, okay, and it has a probability density function. Well, let's try to graph this quite fast. So first of all, let's find what is the expected value of x. Well, the expected value of x is going to be equal to boundary from 1 to 3 of x multiplied by its probability. If you take the integral of that, you will get finally the value of 2. If you do it on your own, you will find it out. What is the variance? Well, let's follow the formula. First of all, we need to find actually the expected value of x squared. 21 over 5. My variance of x is going to be equal to 21 over 5, which is the expected value of x squared, minus the expected value of 2 to the power of 2 is going to be 1/5. I think now we have left only one more last thing to discuss, some special kind of distribution given that the variable is a continuous. That's exactly what we're going to do next. I will see you then.